All right, so tonight we're going to talk about lists, and list is sort of an all-encompassing term for the data structures topic as it relates to Python. Okay, we've got Python to work with. We've got a number of built-in data structures and things like that that we can use in Python. So that's what we're going to cover. So data structures in general, there are entire undergraduate courses on data structure. So we're not going to cover the entirety of what you would think that you need to know for having data structures under your belt. But there are data structures in Python. They're helpful. I want to carry on the theme of there's a number of problems that you're going to encounter that involve data structures. And I want you to know what's available in Python and have an idea of how to approach those problems using Python to solve them. Dictionaries is another example of a data structure in Python. So we'll talk about those. We need to know how to create one of these lists or dictionaries. We need to know how to initialize it with data, whether we input it from the user, whether we read it from a file, whatever. We need to be able to put data into them, iterate over them, understand a problem that's going to require us to reach out to one of these data structures, how to implement an algorithm to solve some problem once we've got them. So there's multiple kinds of lists. One-dimensional lists are the most common. You have two-dimensional, think a spreadsheet or a table, like a tic-tac-toe board, chessboard, something like that, data that you need that's in tabular form. So there are use cases that involve getting the data, how to put it into a data structure like a list once you've got it, how to take a data structure like a list full of data and output it to the screen, output it to a file, wherever you're going to send it. And then there are a number of standard patterns for iterating over a populated list. So we'll talk about those. We have, like with all of the variables that we've created up to this point, there's been, I think we even discussed this early on in one of the early lectures, that you can take your variable and say dot type, and you can find out what type it is. Is it an int? Is it a float? Is it a string? And we pointed out how lists and dictionary were data types that come with certain kinds of objects when we talked about the type method. Looping. We love repeating things. Yep. All this kind of stuff. Good stuff. Okay, when we talk about data, there's a couple of different things that we need to be aware of and think about. Some data is homogeneous, where when we look at the data in the list, it is all the same type. For example, maybe we have a list of 10 elements and every one of the elements in the list is a string. Very common. But in Python, you're not expected to adhere to that. You can have a couple of ints, then a couple of strings, then a float, then another string. You can mix and match. Python doesn't care. It has a list of things, a list of objects, if you will. And what those objects are, int, string, float, whatever, it could be another list. One of the elements of your list could be a whole nother list. It doesn't care. So while that provides a great deal of flexibility to you as a programmer, it also requires some responsibility to think about the fact that, well, I might have accidentally put a string and an int next to each other. So when I'm printing those, I might have to convert it from an int to a string if I want to print it. It might not already be a string. So you have to be flexible and robust in your programming activities to make sure you account for that it's non-homogeneous. We would call that non-homogeneous or heterogeneous is the terminology that you'll see. So if it's homogeneous, it's because you as a programmer put the same kind of data into the list. If you didn't pay attention to doing that, you should always write your code to expect the data to be heterogeneous or non-homogeneous and just take care, otherwise you'll end up with problems. Well, this usually presents itself as when you get a bunch of user input or you read data from a file and all of your testing is, you think, oh, well, it's supposed to be integer data. And so you always enter integers at the prompt and you always put those integers in there. And then as soon as you give it to your little sister to test for you, first thing they do is they put in a string and your program crashes and you're embarrassed, okay? That's where this kind of thing usually happens. So if you know that that's a possibility, you can make sure that you test with values that include other data types and make sure that your program is either preventing those from getting into your list or handling that should they get in there from some other means that you didn't expect. That's the main point here. Yeah, and we're not talking about the values. The values will always be different. I mean, can and will and probably mostly will be different. We're not talking about the value. We're talking about the type of that value. Hopefully that's clear. Another thing to consider when you're putting a bunch of data into a list, again, let's say you're getting input from the user on the screen. You're prompting them, keep entering numbers until you hit quit, right? And when you test your program, you put them in there 1, 2, 4, 6, 9, 12, you put them in there in numerical order. So your program may expect them to be in order all the time and iterate them that way. And then the first time you encounter real world data, it's not in order and your program doesn't behave and behaves unpredictably because your expectations weren't met. So consider whether it's ordered. Also, another common thing that happens is that there's a difference between sorting data numerically. If you sort the values 1 through 100, the 1-digit values are going to come first, the 2-digit numbers are going to come second, and then 100 has 3 digits, it'll come at the end because that's numerical order, right? If you sort strings, strings don't care about the number values. The word apple comes before the value 10. The value 10 comes before the value 2, surprisingly. And that's unexpected a lot of times by people. So keep that in consideration. I've got some examples here. So this is just a bunch of strings that I typed into Excel. And you notice how they are sorted. The first one is 1, then it jumps to 10 and 11 and 12, then back to 2, because when considered as a string, this is the proper way to sort a string of characters, right? Similarly, back here in the rack number, rack 10, all the rack 10 values come before rack 2, right? So this can cause some odd results and stymie you as to why your program is encountering bugs if you don't realize and expect it. When you see this, you realize these values are all being sorted based on their character, their string value, not on their numeric value. Same with File Explorer. When you look at File Explorer, whether you're looking at a list of all your MP3 files or a list of PowerPoints in a folder like the one I found, same thing. 1, then 10, then it goes back to 2. These are being sorted on their string value. Okay. Now, at Microsoft, when I was working with a lot of virtual machines, that got annoying to me. All right. So if you are working in an environment where you use Hyper-V, the Hyper-V manager, I fixed this bug. So I don't sort these based on the character name of the VM. It sorts them properly. Because dang it, I had a bunch of VMs and I didn't want them to sort that way. So I just approached the manager of the team that owned that code and I said, do you mind if I just fix this? They said, yeah, sure, knock yourself out. So if you are running Hyper-V, it's smart. It doesn't sort them improperly. It goes 1, 2, 2, 10, 3, 8, 10. It sorts them kind of combined. It'll sort the character's character, it'll sort the number's number. Yeah.
So you're saying that so instead of like lab 1, lab 10, lab 2, it'll be like that?
Right. Right.
And then related to like the binary code, the hexadecimal?
Yeah, it's so when you're looking at character data, strings, the number that you see on the screen is what it displays, despite the fact that in memory, it's using the ASCII value for that character. So it's sorting it based on the ASCII value in each position. And so that's the way it works. So anyway, I was happy with doing this, that they let me do it. It's one of my little things, my legacy of being at Microsoft that I can be proud of. So you're welcome if you have to use Hyper-V in the future.
You did that?
Yeah.
If I go on Hyper-V.
If you run Hyper-V and you create a whole bunch of VMs, they will sort them properly.
Was it like a weekend fix or a couple of days?
It was a couple of days, but the process to get any change into Windows takes probably at least 2 to 3 months. So, okay. So repeated data in general. So when we're programming, we encounter lots and lots of situations. I've proposed a couple of them here. You're working at a car dealership and there's a whole bunch of cars you're trying to sell, and you're maintaining data on each car that's out there in the parking lot. Or again, your MP3 folder, you have a bunch of file names in a folder on your hard drive. You're getting ready to go to the store and you check with Alexa, hey, what's on my shopping list? There's a bunch of items in there. I guess one of the questions I would ask is, how homogeneous or non-homogeneous are these sets of data? So if we think about cars in a parking lot, is that, if I have a list of cars in the parking lot, is that homogeneous data or non-homogeneous? Or heterogeneous, non-homogeneous? Yeah, again, so that's different values, right? But if I have a list of cars, yeah, would they be the same type of data with different values, or would they be different types of data?
Same data with different values.
Yeah, I would probably nod to that. Yes, they're going to be the same kind of data, but different values for each one of them. If I had, I could imagine ways to make it non-homogeneous, like we have pickups and sedans, and maybe the pickups, I need to have a property that says that they are four-wheel drive or not. Maybe the sedans, I need to know whether they have a sunroof or not. So they might have attributes that apply to some of the objects in the list and not to other objects in the list. And you can introduce non-homogeneousness to your data if you work at it. But if we boil it down to, we figure out a way to represent each item in the list with a string. Now they're all strings. So now they're all homogeneous again. And that's one of the challenges that programmers deal with when they're dealing with data. When we get to solving problems like this for real, you're probably going to get into more of like an object-oriented programming, and Python supports defining classes and objects. So you can read that chapter on classes, and then classes can have different properties like sunroof, yes or no, name of the automobile, things like that. You can bring it back to being homogeneous with the same properties on each object. You can manage it that way. But that's probably a topic for more of an object-oriented class or a system analysis class. Yeah. So anyway, I think that's the point I was trying to get by there. Another thing I wanted to go over is the fact that most of the programs we've done up to this point they follow a pretty simple pattern. I even tried to emphasize this as I graded some of your programs that you turned in. We do our inputs, we get the data from the user, we put it in a variable, maybe several variables. We do some processing on that, maybe that results in more variables with data in them. And then we do output, where we take all the data in those variables and we output it. Very simple: input, process, output. What's more common is more complex problems, sure, but a slightly different pattern is to input a bunch of data and store multiple pieces of data in memory at one time. Then once you've got that data sitting there in memory in a, let's say, list or a dictionary or something like that, then you process it, and maybe you process it again, and maybe you process it again multiple times. Then you iterate over that data to output something to the screen. And we'll go over some examples of that. But this is going to be a more common pattern that you're going to run into for problem solving. So it's good to really get the whole idea of lists and dictionaries down pat, because it's going to be very commonly something you run into. Yeah, and stacks and queues, I'll introduce that terminology here now too. Python doesn't really have the notion of a stack or a queue with an asterisk after it there. They do, because what they say is use a list to implement logic that requires a stack or a queue. Okay, so again, it's one of these things where they've got a very flexible list object, and then it's up to you to use it properly as a stack or a queue. And I'll go over what those are and what the differences is. So, but pointing out that when I use the term data structures, like I said, that's more of an umbrella term, and lists, dictionary, stacks, queues, all those things fall under that umbrella. They're all data structures. And that's nothing more, they call it a data structure because it's a structured place for you to hold your data in this pattern so that you can process it or output it later. And there's lots of problems, lots of kinds of data that we come in, like the examples that I have up there. And so that's why we have so many data structures, because we try to make it easy on ourselves to write our programs and write algorithms that process this data in a form that's conducive to that. Okay, so here's a simple list. It's a list of what? Strings, right? Of type what? Strings. So yes, they're colors, but it's essentially a list of homogeneous data. All the types of each element in this list is a string. So we've got homogeneous data. Okay, so we're going to, we want to print all of the items in that list, let's say. So we've seen while loops before. We've written programs with while loops a number of times. So this pattern should be familiar. Does that look okay? So I set my loop variable to 0. While my loop variable is less than the number of items in the list, I print that item. And then I update my loop variable. So if you take the fact that we're introducing lists out of this, this is nothing more than a typical while loop. It has all the rules: set your loop variable, while loop condition, update your loop condition inside the loop. No different than what we've been doing. Well, what we've introduced is colors is a list. I know it's a list because I'm initializing it with something that is inside square brackets. So anytime you see something inside square brackets, you know you're going to be dealing with a list, an object of type list. So if I, right after this line of code, if I said colors.type, it would output it's a list. Okay. The next thing I see in here is I've got this length function. This is a built-in function that is designed to tell me how many elements there are in this list object. So all of the list objects that you'll create in Python can be passed to the length function, and it knows what to do with it to count how many elements there are in that list and return it. So what's this one going to list? Return. Quick count reveals 6, right? Not 5. I thought these were 0 based. Okay, it's got 6. So that's how many elements. So the length will return 6, but the indexes, the index values of the elements in the list go from 0 to 5. It's 0 based indexing, but there's still 6 elements in the list. So length returns, and remember we're using the less than. So while our loop variable is less than the number of times we want to loop, so we're going to be looping 0 through the count -1, or the length -1. Make sense?
So how would it run?
I think it runs very well. In what aspect were you referring to?
Like, how would it where it run?
Well, that's a great question. So I think we should desk check this. Okay. The next thing I want to point out here, though, is how do we access individual items of the list? And that's using this syntax. When I use the name of the list and square brackets and a number 0 through 5, I will get the corresponding element from the list back as a string, because that's what it is a string.
You're saying the square bracket index takes anything off the dictionary or the list?
Off the list in this case, yeah.
The square bracket index.
Yeah.
Where it's on the
And that's why I'm pointing these things out, because this is how it works in Python. This is the rigid, non-flexible syntax that you have to use to deal with the list. This is how you initialize it. This is how you find out how many elements are in it. This is how you get an individual item out of the list. And the rest of it is just plain old looping logic that we're already familiar with. Okay, yeah, so that should output each of the colors of the list. So let's prove it up to ourselves. So I won't write colors up there, but we've got variables index. Yeah, that's pretty much it. Colors and index. All right, so I start out and I set index equal to 0. While is 0 less than 6? Yes, so we keep looping. Print colors index. So colors, and the terminology, the way you read this out loud is colors sub 0. We also refer to this index as a subscript of the list. So that's why we say colors sub 0. So color sub 0 would be red. So we're going to print red on the screen. We go down, index equals index plus 1. Go back up, 1 is less than 6. We print color sub 1. And so on. So then we get up to, let's say 5, index equals index plus 1, we get to 5. We go back around, is 5 less than 6? Yes. So we print color sub 5, which is orange. Index equals index plus 1, 6. We go back up. While index is less than color, so 6 is not less than 6, that's false. So we break out of the loop and we're done. Yeah.
So where it says index to 0, that just sets it for the first one, the red.
Yep.
It's red is 0. That's the first.
Correct. I mean,
also,
literally, all it does is puts the value 0 into a variable called index. That's
right.
all this is doing.
What if we would, because I believe I've used this before, like I put a variable into like square brackets instead of 0, and it just like it just use a 0 or like a set.
Mm-hmm.
out when I use square brackets, is it run the same or?
What do you say? So if you say color, sub, and a number instead of a variable?
The index equals 0, and we did index equals the square bracket.
Oh, okay. So this is a different syntax that we haven't gotten to yet. But if you're reading the book, you'll notice that if I say variable equals and square bracket, square bracket, all I'm doing is I'm saying I want to create an empty list with no elements in it and put that into this variable. Now, if I say var.type, it's still going to say list, but if I say length of variable, it's going to say 0. There's nothing in it. So then I've got an empty list, and you'll see that in a little bit. Yeah, it's a common pattern. Like I said, you'll see it. Anybody have a problem with this? You believe it works? Okay. We'll go on to the next way to do this. So this one, let's say we want to print all of the colors, but we want them all on one line. Okay. So what I'm going to do here is use the pattern we did in one of our programming assignments. I'm going to pick a string variable, all colors, and I'm going to set it to blank. And I'm going to iterate over this list a different way for color in colors. Okay, digest that a little bit. So colors is the name of my list. That's what I'm iterating over. And color is a new variable that I've created. So all colors is one variable, color is another variable, and colors is my list. Okay, that's all that's happening here. I want to point out, like the comment says, when you use it in this way, what Python does is it says, well, in what? In something I can iterate over. And we've seen that in previous programs where it used the range function to create a set of numbers, right? Well, that's all it's doing is it's saying, hey, colors, can I have a range object that represents all the elements inside you? And so it returns a range. So this is range syntax. Okay, so for each color in colors is what that says. And I'm going to append this particular color to the end of all colors with a space in between them. We've done that before in a previous program, so that should be new. And that's it. So 4 lines of code versus 4 lines of code, which one do you like better? Yeah, well, they both do exactly the same thing. If you're very comfortable with writing while loops, probably feels very familiar, like, you know, a snuggly blanket. You may like this one better. But, you know, this one is pretty elegant syntax too. We don't have to maintain our own loop variable. We don't have to make sure that we did less than instead of less than or equal to. You know, we don't have to be unsure of whether it's going to iterate over the list correctly. Yeah.
For the for loop, why not change the print statement that end equal and then open position to remove the next line?
Yeah. Yeah. If you know how to do that, yeah, sure. Yeah. What he's saying is you can eliminate this. You can eliminate this by putting a print statement here with some fancy Python stuff. And then you only have 2 lines of code. But without Python magic, you know, this is a pretty simple way to iterate over the list. And it's a very common pattern that you'll see. And it's very consistent with what you're able to do easily in other programming languages too, which is why I lean on this one. It also, again, one of the concepts about programming that I'm trying to point out is if you can get into this way of programming the problems in your mind where you think, I'm going to set the value of a variable, and then I'm going to update the value that that variable has in it over time. If you can master that concept and use that pattern, it'll serve you in a lot of situations in the future. Because again, it's like I put on the earlier slide. There's a difference between the simple patterns that we've been doing up to this point where you get one piece of data, you process that one piece of data, you output something, and then you forget about that piece of data and move on to another piece of data, right? That's a very simple elementary pattern. This is more complex because there's a temporal dynamic to the program as it runs. That variables have different states at different times in your program, and you need to make your brain be aware and conscious of what those changes are that are happening. You know, what's the value of all colors? Well, it depends. Up here, it doesn't exist. Here, it's blank. Here, well, it's going to change throughout the iteration through the loop. And then I'm going to print the whole string at the end. You know, you just need to be aware of that. So I like this pattern. You want to see another, even better way to do this? Is to just say print colors. This does the same thing as these two. Because the print function, guess what? The built-in print function, it knows about range syntax too. So when it's passed a list, it says, oh, well, can you give me a range over that list? And I'll just print each one of them for you. So boom, there you go. One line. The other thing I want to point out is you have to be careful. It's up to you as the programmer. You know, I've got 6 elements in here. Indexes 0 through 5. And if I use a number that's outside of that range, -12, 436, 99, when this line of code executes, you're going to get one of a variety of errors. It's different languages say it in different ways, but subscript out of range would be a good one. Index error would be another one. So anytime you get an error like that, you know that you passed the wrong number. Usually it'll be, oh, I had a typo in the number that I put in here, or, oh, I used the wrong variable, or, oh, why did I multiply my index times 2 on that line? What was I thinking? But that's the kind of thing. Look at this variable and trace back what the value of it was. And a good way to diagnose it is if you're using a variable here, you know, like this, just put a print statement in here and print index. And that way, before it tries to execute this line, you can see what the value of that variable was. The other thing, I think I pointed this out. Colors is a one-dimensional array. It's a simple list of values, homogeneous values, but it's one-dimensional. So there's some other operations that we can do. Sometimes, like you're pointing out, you want to use a pattern that involves starting with an empty list and appending to it. So if I've got this list of 6 colors from the previous example, I can say append, and I can append another element to the end. So after I execute this, the length goes up by 1. It was 6. Now it's 7. And array values 0 through 6 will work now. And colors sub 6 will give me fuchsia. Similar thing, so going to the example brought up, here's a loop that will get them iteratively. So I start out with an empty list, and what does this do? Loops forever, right? So how am I going to get out of the loop? Probably going to be a break statement down here somewhere, right? Common pattern, we've seen it before. So on this one, each time through the loop, we ask them to enter a number. If it's -1, we break and get out of the loop. If it's not, then we just append it to the end of the list. Well, now I can ask for any number of values from the user, and they can keep entering integers till the cows come home. And when I get out of this loop, I don't know how many values there are. I don't know if they're homogeneous because the user entered them. Now I was clever, and and I wrap this with an int. So now I'm back to being able to count on the fact that values is going to contain homogeneous data and they're all going to be integers. Right? So this print statement says, hey, here's how many you added, because I'm going to use the length function, or the length function on values. That'll tell me how many of them there are. And then I stringify that and say you entered 12 numbers or however many they entered. And then this one is the convenient way to just say, hey, print all those values. Any questions about that one? Pretty cool, huh? That's a common pattern too. Start with an empty list, let the user fill it, and then we go on to processing it. And that's the thing. See, before, we would have had to have done all of our processing inside this while loop after we got each value. You know, when we were computing the sum, we had to add each value to our sum. And at the end, we could print it out. But here, we can make this step one is get all the values from the user. Step two is go through it and add them all up. Step three is display them all. We can break it up into separate operations. Much more flexible pattern. Okay, there's various ways of processing items in a list, like using it as a range, like we talked about. Let's talk about one of them. If I want to add up all of the numbers in a list, they're all integers here, and here I'm creating a pre-populated list, but I could very easily replace that line of code with the program from the previous slide and get a bunch of numbers from the user. So this is basically looping through all of the values and adding them up, and then printing the sum when we get done, right? Here's another way to do that. Should feel very familiar and comfortable. I set my sum to 0, index to 0. I loop while my index is less than the number of items in the list. I add them up. I modify my loop variable. And then at the end, I print my sum. Do the same thing, right? So you can probably guess I'm going to show you an easy way to do that, right? Yeah. Yeah, I'm adding value to sum is the way to read that line of code. Add value to sum. So for each value in values. So each time through the loop, it's automatically going to set value to the next value in the list. Very convenient. Okay, so now, spoiler, there's a really easy way to do this because there's a built-in function called sum. You pass it a list, it does that for you. It does basically the equivalent of these two. It does it for you. Pretty cool. Okay, so if we want to, this is something we haven't written a program for yet, but if I have a list of items and I want to process, let's call it selectively, like let's say I want a program that gets a bunch of values from the user and then tells me how many times did the user enter 17. Kind of a made up program, obviously, but here's a list. I'm pre-populating this list with a bunch of values. You can see a few 17s in there. So I need to write a program that goes through. If the value is equal to 17, I add 1 to my counter. And then at the end, I say, hey, this is how many 17s that the user entered. Well, there's a count function on the list that will say, hey, you give me a value and I'll look in that list and tell you how many times that value appears in there with one line of code. It's really nice. as you can imagine, they provide these common built-in functions because you run into this need a lot when you're programming, and you don't want to have to write it yourself. So this is the big question. Is one better than the other? Should I use the built-in function all the time whenever there's one available? Should I do it myself so that I know how to do it? I mean, if this is just as good as that, then what's the difference? Does it matter? Well, yes, one of them is faster. The built-in functions are probably written in C++, where your lines of code are written in Python, and the C++ version of it's always going to be faster, sometimes orders of magnitude faster than if you coded it yourself. So yes, in Python, anytime you have a built-in function, you should always use it instead of that. There are other really good arguments, even if you were writing your program in C++ and it's equivalent performance-wise, you would want to try to use the built-in function when you can, because things like somebody else already tested it, right? Somebody off at Microsoft or Oracle or someplace has already written that code and tested it, and millions and millions of developers have been using it. And unless somebody broke something last Tuesday, it's probably working. Whereas yours, you have to stop and think about it, and you probably have to test it for a couple of hours. It's much more economical to use the built-in function when one exists. And so here's a little table of a bunch of the built-in functions. You know, getting the min value from a list, the max value, and that works whether it's strings or integers. Sum, count. This one's nice. Like if we want to know the index, where is the 17 in the list? You can use the index method to find it out. And then the sort, that one's really helpful too. But you have to be careful using this. Be judicious about when you do sorts, because they can slow your program down if you're sorting all the time. You don't want to do a sort and then append a value to the end and resort, append another value to the end and resort, because after that list gets so big, it's going to be very slow to continually add one more item to the list. There's other algorithms that you can use to insert into a list as opposed to appending and sorting and things like that. But it's there, it works very well, and use it. Some things in Python you can take advantage of. I won't dwell on these too much. There's a lot of different variations, a lot of advanced syntax. You know, I had to, in parts of my career, use the Perl programming language. And Perl is one of those languages, I would describe it as programmers daring each other to come up with more obscure syntax ways of doing things. And if you could come up with a way of doing something in Perl that another programmer couldn't understand, then you win. And it was like a contest like that to see who could make the most confusing, unreadable code possible. That's the main reason I don't like Perl. It's not readable. You know, when I say things like, oh, you read this line of code as this, you can't even read Perl often. It's just too undecipherable. It's very easy to become good enough at Perl that you can write code that very few other people can read. And that makes it very hard to maintain and update reliably. But Python tries to go that direction. So my guess is a bunch of the people that worked on the Perl language decided that Python was a shiny object and moved over there and started trying to add all those same kind of bells and whistles to Python. So just beware of that. Make sure if you're going to use some of these Python specific syntax that don't appear in other languages, maybe a courtesy comment around it to say, this is what this line of code does for other programmers. And you always have to assume, even if you're the whiz-bang programmer on the team, next month they're going to hire a junior programmer. You know, they're going to have an intern in for the summer, and they're going to be maintaining this code while you're not watching. And you want to make sure that it's written in such a way that the interns aren't going to break it. Okay. But we'll talk about it. So let's say we want to know, I wanted to do something with all of the even numbered values in this list. So we've started out, I've got an empty list of evens, and I'm going to traditional, easy little loop. I'm going to loop over all of the items in the values collection. Okay, remember our little modulus operator that tells us the remainder? So if I divide something by 2 and the remainder is 0, it's even. So it's just a clever way to say, hey, is value even? And if it is, I'm going to append it to my evens collection. And then at the end, I'm going to print the evens. So everybody buy the fact that this is a decent way to write this program if I wanted to get a list of the evens and print them from that list? Okay. Well, there's a Python-specific way of doing this. I color-coded it so I can break it up and explain how this works. You can just say evens equals value for value, and values is value mod 2 equals 0. And that will do the same thing as this program. So the way this syntax works in Python, the way you break it down, is here's what I want. Well, let's forget this for a minute. Let's go to the middle part. This is simply just my loop, right? Here's how I want you to iterate. And all you have to do is provide something that produces a range here, right? For each value in this list, I want the value. That's what I want. That's my result. But only if this condition is satisfied. Okay? You put your condition here. You put your loop part here, and what you want out of it here. Okay? And if you do that this way for this collection, it gives you the exact same result as this program here. It's clever. It's a nice way to write it in one line of code instead of 5. But is somebody else going to be able to read and maintain it? Maybe. Here's a challenge I'll give you if you like playing with stuff like this. Instead of printing the actual values, the 4, the 14, and the 52, give me the indexes for each of those. See if you can come up with a way to do that in Python. That will be a good challenge. And if you're able to do this, it will show you understand the syntax and can manipulate it well. So instead, I would want 0, 4, and 5 as my output. I'll leave that as an exercise for the reader. Okay, so now we're going on to two-dimensional stuff. So if I was inputting from the user, let's say a multiplication table, I wanted to produce a multiplication table. We had a program like that, right? Or if I want to keep track of which piece is on the chessboard in each thing, or Othello or checkers, then it's two-dimensional tabular data, so we need a two-dimensional data structure. I know that we don't want to, for the chess example, we don't want to declare 64 variables. That's not fun. And we wouldn't even want to declare 8 lists, one for each row. So what we really need is one two-dimensional, think of this as a nested list, a list within a list. So initializing one, we use nested square brackets. So if I have this grid, I have my outer square brackets and, 3 values inside that list. So it's a list of 3 values, and each of the values is a list of 3 values. So it's a 3 by 3 list, 3 rows, 3 columns. That's how you initialize it. If you were going to start and build one up programmatically, you would do something similar to what we did before. where you'd say my grid equals an empty list. And then you say G dot append empty list, right? So I've appended one empty list inside the empty list. So G now has length 1, right? Length of G is going to return 1. But then length of G sub 0 also is 1. Well, actually, no, it's 0 at this point, right? Because it's an empty list. So I'd have to say G sub 0 dot append, I don't know, number 5, let's say. And now length of G sub 0 is 1. That makes sense? It's not magic, it's just nested lists. It's a list of lists. Is there anything that says that I can't have a list of 2, a list of 5, and a list of 1, maybe another empty list? No, that's up to you as the programmer. If when you're collecting your input, you make sure that your algorithm puts the right number of row lists in there and the right number of elements in each one of those, then your program can count on that. If your program fails to ensure that, or you're getting the data from the user or from a database or from a file, then your algorithm needs to be aware that it needs to check and do everything based on calling the length function and seeing how many elements that has before you go off iterating. Otherwise, you'll drive yourself crazy with subscript out of range errors when you run it. So here's another nice little thing to see is if I want to build a 2-dimensional list, list of lists of zeros, starting with an empty list like this. So I start out with an empty list. I ask the user, how many rows do you want to create? How many columns do you want to create? Now, we have nested loop, right? We iterate over the rows. We iterate over the columns. For each row, we add an empty list. And for each column, we add a 0. Now, when I print this matrix, I'm going to get a table of zeros. Probably not formatted very well, but there you go. Okay, changing gears a little, moving on to dictionaries. If you think about the word dictionary and the definition of that, it's pretty intuitive. We're saying I'm going to give you a value and you're going to look that up in this other list and you're going to tell me what value is associated with that key value. Okay, so you're given a key and you produce the value associated with that key. If you're looking in a dictionary and I give you the word dog, you would expect to see a definition: dog, noun, 4-legged furry object, man's best friend. So it's pretty intuitive and it is what it sounds like. So where lists are declared using the square brackets, dictionaries, just to make it interesting, use curly braces. Why we call one brackets and the other braces, I don't know. If you said curly brackets and square braces, I'd say, yeah, okay. But other than that, they're very similar. So in order to initialize something called scores in a variable, I know that's a dictionary because I'm using curly braces. The syntax is you give it the key value, colon, and the value. So key, colon, value. If I want to get Jessica's score, so I'm using Jessica as the key, then I say scores sub Jessica, and that's going to return 3. Are any of you wondering why we don't use curly braces here? Right? It seems like for being consistent, we use curly braces to define it. Why would not use curly braces to access it? I don't know. Ask the Python people. But you just have to know in the rigid rules of how to code Python, you have to use the curly braces to define it and initialize it. You have to use the square braces just like lists in order to access the element. Yeah, this is another interesting thing. You can say, hey, give me the keys, the list of keys. And what this is going to give you back is scores.keys gives you back a object of type list, not dictionary. And it's going to contain 3 strings, Bruce, Jessica, Fernando. You say scores.values, likewise, it's going to give you a list of 3 integers, 6, 3, and 7. Could I have put the word dog here instead of 3 inside double quotes? Yes. Again, that's up to you as the programmer. Garbage in, garbage out. If you make sure that it's got structure going in, you can rely on it having structure when you iterate over it. If you don't, you can't. You should probably just remember this. Dictionary objects, whether they're in Python, C#, it's a common interview question. Dictionaries use hash maps because they're really efficient. They're really fast to access. Hash maps have a constant time insertion performance, and I think it's order log of n retrieval. So you want to use hash maps, and dictionaries in Python, dictionaries in C# use hash maps. Java use hash maps. Actually, in Java, I think it's called a hash map. It gets confusing. But if you want to know more about that, there's a nice page on W3 Schools. I don't have time to go through it in class here, but it'll tell you about hash maps and why hash maps are awesome and why Python uses hash maps and what it means. Stacks and queues I mentioned. So the main way to remember it, for me, it works, is a stack is like a stack of pancakes. Waitress brings you a pancake, she brings you another pancake, puts it on top. You can't eat the bottom pancake until you eat the top pancake. It's the last pancake onto the stack is the first pancake you eat. So last in, first out. The queue, in England, you stand in a queue when you go to the bank. Here in America, we stand in a line when we go to the bank. Yeah. In the drive-through, we line up in the drive-through. They queue up in the drive-through in England. So, but yeah. So, but that's why it's called a queue, is because you queue up elements. And the only thing there is, as opposed to the way the stack works, if you're the first one into the drive-through, you're the first one that gets your food to leave, right? It's first in, first out, as opposed to a stack of pancakes where it's last in, first out. Yeah, so we don't have objects. There's no, square brackets for a list, curly braces for a dictionary, asterisks for a stack. No, we don't have any new way of declaring those. You're just going to declare a list with square brackets for a stack or a queue. You just implement the logic that treats them that way. There are methods, push and pop, that you can use with them. And I would say also, if you want to know how to use those better, you'll get into those in future classes, future programming classes. You will encounter them. You'll be asked about them in interviews. But there's really nice pages on W3 Schools that you can read that'll brief you on that. Okay, and so that's most of the stuff that I wanted to talk about with lists. Any specific questions there? What was the question? Can we practice some? You want to see them actually run? Let's see. Think of a problem.
1200?
Something that I can solve using a list. Okay, that sounds pretty good. Let me collect items for a grocery list. Let me make this bigger so we can read it. Is that readable? Okay. So I'm going to say groceries equals open brace, close brace, right? Where we declared and initialized an empty list of groceries. So if I quit right here, run this, then I get open brace, close brace as my output. It's just an empty list, right? So let's use the while forever method maybe. While true. Item equals input. What do you need from the store? Quit to stop. Because that's what I'm going to expect. I'm going to say, if you want to stop entering items for your grocery list, then enter quit. So now I've got the value. I'm going to check if they entered quit. If item equals quit, break, go away, we're done, right? If they didn't enter quit, then I want to add this to the list. That sound reasonable? Let's run it and see what it says. Okay, what do you need from the store? I'm going to type quit the very first time and make sure it doesn't crash. I get an empty list. Run it again. What do you need from the store? Eggs, milk, potato chips, pretty much my standard store list. And then say quit. And so it printed my list, and here's what I got. What would be another good example? Yeah.
Can you show a flow rhythm of making a list? I don't have problems with that.
Good question. Let's see what we run into here. Again, apologies. Oh, I guess I can zoom in. Sorry. I was going to apologize for not being able to zoom in, but I forgot that I can zoom in. Okay, so let's see. Declare an array of size. I don't know. This may be a limitation of Flowgorithm where you may have to say like, okay, I'm going to say it's got 99 elements in it. I don't know. Let's say 0 and see if we can do it. And they're going to be strings. While loop, while true. I want to input, enter item. I'm going to be more brief with this. I already did the long version in the code with all the nice prompts. So here I'm going to use brevity to make it simple. So enter an item. Oh, wait. Oh, enter a variable name, item. So I guess if I wanted to do my prompt, I'd have to put a print statement here that says enter an item. Output. Yeah. So now I want my if statement there. If item equals quit break. I haven't. Yeah, see, as I explained before, this whole break logic isn't considered structured programming. We don't really do that. It's just, so break, when I see break, I think go to. Says if item equals quit, go to line 14. And go tos are how you know you're not doing structured programming if you have to use a go to. It has been somebody long ago, like in the 70s, I think, mathematically proved that any program written using a go to can be written the same to do the same thing without using a go to. At that point, the entire industry said, okay, well, then we shouldn't allow go tos because they lead to unstructured programming. One of my first tasks when I got out of college, I was working for the airline TWA that no longer exists, but it was a reservation system, and I had to write code to update this report that was printing these invoices. So when TWA would book cars on behalf of, let's say, Avis Hertz budget, then at the end of the month, they would send an invoice, and TWA got like $2 per rental car that they booked on behalf of each airline. Some rental cars, it was $2, some it was $3, different amounts, but they'd have to produce this huge long invoice. It was hundreds of pages long for each airline or for each car company. And TWA would send that to the car company, and the car company would write a check for the booking fees back to TWA. Problem was, the report was on triplicate carbon paper, and they were running out of it. The company that made it didn't want to make it anymore. And so they had to come up with a way to print the same report on 8.5 by 11 white paper. And so I had to make changes to it. Next problem was the source code for the program didn't work. Couldn't even compile it. It had nothing to do with what was actually being run every month in production. And at least 3 people had worked on this program and given up and threw it on the pile and said, I can't get it to work, before they handed it to me. So I was given a non-working code for something that was running out of time and had nothing to do with what was actually in production. And I had to go through the hardest thing about it was you couldn't follow the logic, because it would have 6 or 8 lines of code and then a branch statement, which is assembly's version of go to, and would branch to somewhere else in the program, maybe hundreds of lines away. And it was spaghetti code. It was branching here and there and everywhere. And you just had no confidence that what you were going to change was going to work ever. And that sold me on not using go-tos. So yeah. So what this exercise tells me is, if you're using this break logic for your Python algorithm, there is no equivalent in logarithm. You're going to have to go back and do it the structured way, where you let's see if we can rework this. So we ask for a value for item, and then while item is not equal to quit, we process that item. We don't check to see if they entered quit and break. while it's not equal to quit, then we append, and then we ask, we modify our loop variable, we ask for another item. This is a structured way of doing the same thing, but you'll notice the deficiency here is I have to ask this question twice to make my code work. Another variation of this is the most compact way. Another variation of this that I've seen some of you use, which works just as well, is you set the string to blank while not equal to quit. Well, it's not equal to quit, so I keep looping, but now I just have to change the order. And I also have to put another if statement here. If item is not equal to quit, then append it. That's also structured. I like the previous one better because I don't like asking if the item is not equal to quit twice. I'd rather ask for the input twice. So I'm gonna undo. Yeah. So I like this pattern better. Now that I can do either one of those in Flowgrid. Yes, it's going to be different. We'll go back to nothing. We'll say, oh, I have to declare item, don't I? Because it's Flowgrid. Yes, item string. I probably have to assign it. Item is blank. Then I can say while item is not equal to quit. Have to end it. Sign. Now, how do we do this? How do you append to an array? Okay, so Flowgrid also doesn't have the append method. Okay, I can do this. Yeah, basically. So I'm going to create a variable called index. I'm going to assign it to 0. So now I know where I'm going to insert it. While item's not equal to quit, I'm going to assign groceries sub index equals item. Ooh, it took it. I was half expected to have to go to Google and find out how to do that assignment statement. And then I have to ask again. Oh, wait, I didn't ask, did I? Oh, yeah, so this needs to be an input. Input. Variable name item. Items I will quit, add it to my list, and then input item again. What do you guys think? Will that loop work? You don't think? What's wrong with it? Oh, I do see one thing that's wrong with it. I never updated index. It's going to rewrite the first element. So I have to say index equals index plus 1. Now it'll increment that each time I put an item in there. And then, of course, when I get out, Output. I wonder if Logarithm will let me output an array. Okay, let's see. Value is not valid and valid 0 is not valid for, yeah. Okay, so I'm gonna have to do 99, let's say. Okay, eggs, milk, cheese, quit. Output shape requires the expression field to be string number. Yeah, I'm guessing that the problem there is Logarithm doesn't know how to output a list, an array. And so I'm going to have to do the loop myself. I have to do a for loop? Are you kidding? This is 2024, people. For index, index 2, 0 to index, step by 1. Output, groceries, index 2. Do I have to declare index 2? Dang it. Maybe? Eggs, milk, chips. Quit. You attempted to read data from a variable for any data. So,
No. Oh, because you set it to 99, but there's nothing else.
Yeah.
It's 3, so it's upset.
well, I think it's because I added 1 to index one too many times. So index is sitting here. If I printed right here, if I output index, I'll bet it's 4 instead of 3. Eggs, milk, bacon, I like it. Quit. No, it says 3.
I think it's because it goes to, because you set the array to 99, it goes to 4, but doesn't see the value in there. It's upset by that.
Maybe it's just the fact that I have to say index minus 1. 0 to, yeah, that's what it is. It goes 0, 1, 2, 3 instead of 0, 1, 2. It's an off by 1 error. So see, your humble professor even did an off by 1 error right in front of you in class, and none of you caught it. 10 disagulations for each of you for that. Eggs, milk, bacon. Quit. Boom. We did it. So there you go. That is the flow chart to do the equivalent. Okay, and so, yeah, now if you have to do a program that has to use lists, remembering the example here from the video and the syntax will help. Yeah.
You said you'd also take like written forms of the flow chart, right?
Do what?
You said you'd also accept like written forms of the flow chart, right?
Yes, if you're not using Flowgorithm and you feel like, so the problem with people who haven't used Flowgorithm so far is they, in your own hand-drawn flowcharts, I don't care if you declare the items, not important to me. But you have to use the right shapes, okay? And you have to use the right logic, and you have to specify what your loop condition is. So you can't leave anything out, and you can't use the wrong shapes, okay? But yes, you can hand draw them and take liberties in ways that Flowgorithm doesn't support if you want to, as long as you do it right. Okay, but if you're going to do it in Flowgorithm, you got to kind of work around it like this. As long as it works in Flowgorithm. So if you can get the flowchart to work in Flowgorithm, I'm 100% sure you can convert that to Python. Right? Where was it? We can see the view tools. Where is it? Source code viewer. Yeah, there you go. There's basically the outline for your Python program, or your pseudocode at least, which should translate pretty quickly to Python. So, and you also know that if you do your flowchart in Flowgorithm, the Python you produce is going to be considered structured code. There's another good thing about it. Okay?
Yeah. Thank you.
Sure. So I will consider that the end of the lists lecture, and we'll now move on to functions. Okay? So let me close down this PowerPoint. And open up the functions. Okay, continuing on. Woohoo, functions. Release the board, so I don't have the list stuff up here. I know that seems trivial, but what it means is when I'm creating the YouTube and I want to split this up, I can scroll forward to the place where the whiteboard went blank. And I know that's where the second half started. Okay, functions. What are we going to do? So we have several different kinds of functions: built in, imported, programmer defined. The reason why we're doing this is along the theme of the discussion about structured programming with lists. We want to program in a modular fashion, and functions helps us build modular structured programs. And they're just a tool. You don't have to use functions. You can write your code without using functions, but it just has some benefits. So we have these classifications built in, I mentioned. So anything that you can use, like that length function that we use to see how many items there were on the list. You know, I put a graphic up there of a bunch of built-in functions. Anything that you're allowed to use that doesn't require an import statement is what we would call a built-in function. An imported one is kind of the flip side of that. There are libraries out there, you know, data science libraries, NumPy, you know, any number of libraries that you can Google for Python that are bunches of code that somebody else wrote that you can import and be able to reference from your code. A programmer defined is the rest of it. That's what we write. That's our functions. The execution flow of your program. We're going to talk about scope a few slides later, but code that is global outside of a function, you know, it's just global. You know, most of the programs we've been writing so far are just a bunch of global code out of the global scope. Okay. A few of you have either done Python before, or you're using the example structure from the book where you define a main function and then you call it. You know, that's not global scope. It's good patterns to use. I like it, but it's not global scope then. But what Python will do is it'll start at the top and it'll execute all of the code that's in global scope from top to bottom of your file. When it gets to a point where your code calls a function, it will jump to it. It'll execute the code in that function. And when it's done, it will jump back to the next line of code after where you called the function. That's the way it works. You can have functions distributed, littered throughout your code. It's not going to call them when it comes to them. It's going to wait until something further down calls it. Then it'll call it, execute those lines, and return. Okay. So that's a little bit on the flow of the code. When you see it in practice, it's pretty easy. It just is a little hard to describe. This is different than most other languages. Traditionally, will have what we call an entry point. So a C++ program has a main function. And you just know that anytime your C++ executable file gets launched, it will automatically look for that main function in there and it will call it. And that's how your program starts. Other stuff may happen outside of there, initializing the stack, allocating memory, but you don't care about all that. That's just boilerplate. You just know that your program starts when your main function gets called. But like C#, for example, traditionally worked the same way. You had a main function that you would implement, and that would be the start of your program. However, recently they've created a new syntax where you can create a C# program with a bunch of code in the global scope, similar to what Python does, and it just gets executed. You don't have to do that main function. You can just write a bunch of global code. I'm not comfortable with it yet because I've learned C# the old way. I think the reason why it is enjoyed by people that prefer that syntax is you can just open a C# file, a .cs file, and just start writing code instructions. You don't have to create all this boilerplate outside that has nothing to do with what you were there to do. In the old days, that's the way we would rank the maturity of a technology. Like there was one project where I was working on at American Airlines where, I'm not kidding, literally, we had a team of 5 developers on this project, and we knew kind of what we were supposed to build, and we worked for 2 months as a team, and then stopped and went and had a meeting and said, okay, what is it? What features are we supposed to implement here? Because all of that work up to that point was boilerplate, creating the project files, creating all of the initial program structure, writing the code to create a window on the screen. Because back then, if you wanted a window with a menu and toolbar, you had to write the code to draw the toolbar and the menu and to add the menu items and all that. There was not all this automatic stuff that the modern environments give you. You had to write all that yourself, regardless of what the menu items were going to be in your program eventually. So we would call that a very immature, non-robust environment because you had to build a whole bunch of boilerplate code that had nothing to do with what you were getting paid to actually give the customer. Well, with this new syntax or with Python's innate ability to just write a bunch of code in the global scope, it's great, for example, in a student environment where you can just start writing the code to implement the algorithm, turn it in, and I've got a nice, short and sweet piece of code that I can grade. I don't have to scroll through lines and lines and lines of code to find the bit that I need to grade. So it is what it is. Some people like it, some people don't use it. So here's a picture that illustrates it. You got a bunch of, declare, initialize, blah, blah, blah. And then, oh, here's a function call. Okay, so I'm going to call that function. I'm going to go over to where the function is in the code. Maybe it's in the same file. Maybe it's at the top. Maybe it's littered throughout there somewhere. I'm going to execute whatever statements are in that function. And then I'm going to come back and continue on. Same thing. Get to this function. I'm going to go execute it and come back to here. And that's the general flow of your program. Your question? Or instruction? Yes.
Or is it also the
Yeah, stay tuned. No, stay tuned. We'll get to defining these. That's what this is about. Yeah, so what a function is a block of code, a block meaning one or more statements that are set aside for us to potentially reuse. Okay. Another way to think of it is I have this set of instructions that do a specific thing. It provides a purpose, and I want to set that aside because I may want to come back and get that one of these days. Another way to think of it is it implements a contract. Look, if I give you $20, will you wash my boat? Excellent. We've got a contract. We've got an agreement. If you'll do it for $20, hey, I'll sign up anybody in here who wants to do it. But for a function, if I provide you this data, if I provide you these parameters, you'll do some work for me, calculate something, do some processing, and you'll return me something that I was looking for. So, for example, let's say if I pass you this list of integers, you will write the code to calculate the average and the standard deviation, and you'll return that to me. Because I got this list of numbers, and all I don't need to know how you're going to do it. I just need the average and the standard deviation for the problem that I'm trying to solve. So you write a function. Okay, great. You give me a list of integers. I will calculate the average and the standard deviation for you and return it. It's a contract. If you pass me an empty list, I'll ask the user to enter a bunch of values. I'll stick them in the list and return you a full list. That sounds like a good deal, doesn't it? And if you'd had that at the beginning of the semester, wouldn't that have been handy? Have a function that you wrote that says, get me a list of integers. Hey, I can use that all over the place, right? Many of our programs have required stuff like that. Any code that you come across where it's like, man, I seem to be writing the same code, these 3 lines of code, I keep writing them over and over and over again. Perfect candidate for putting those in a function and just calling it each time you need to do that work. I won't say every time you repeat more than 1 line of code, because there's a certain amount of work that the compiler has to do in order to package the parameters, put them someplace, call your code, get those values off and do something with them. That homework that has to be done in order to prepare to call and process the data that comes back, it's not free. It's cheap, but it's not free. So if it's only 2 lines of code, maybe you have to do that 3 or 4 times in your program before you say, maybe I should put that in a function. If it's 18 lines of code, if you have to do that twice, you're definitely going to make that a function. Okay, because there's going to be a big savings there. You're balancing processing time against number of lines of code. If you have your code to do a specific thing in a function, it's probably going to be easier to find that and modify just that part. You know, you'll find often that your challenge is to make a function go faster, but do the same thing. In other words, honor the same contract. Another thing is testing. When you get to where you're writing commercial code, you're probably going to need to unit test your code. And it's so much easier to have a function and provide a whole bunch of calls with different sets of data and see if it returns the right results. It's called unit testing. It's much easier to do if your code is written in functions than if it's not. And we use the term encapsulation. So we're taking some piece of functionality and we're encapsulating it inside a function. And here's another, hint for later is the pseudocode and flowchart. Instead of trying to do that for the huge program, if you do the pseudocode and flowchart for each individual problem, the sub-problems that you're solving, it's much easier to do the project than to try to do it all as one big, huge monolithic one. Okay, defining functions. The parts of a function definition are the return value, the function name, and the parameter list. Okay, that's the 3 main parts. There's something called a signature. That's the part of the function that uniquely identifies it from all of the other functions in your program. And as you might guess, it's bad form to try to have 2 functions with the same signature. That would be ambiguous. The compiler wouldn't know which one to call. And also keep in mind that the return value is not part of the signature. We list it there because it's something important to realize about your function, but mainly the function name and the parameter list are the signature. Return values are one of those things in Python that they play fast and loose with. Same as with the lists. Does your we don't use the term homogeneous and non-homogeneous with respect to return values from functions, but it's the same kind of dynamic there. You can call your function and have an if statement in there, and one path returns an integer and the other path returns a string, and Python doesn't care. But the code calling it might care. If the code calling the function is always expecting it to return an integer, and then all of a sudden it returns a string, boom. So it's exactly the same theme as before with lists. If you take care when you're defining your functions, then you can be relaxed when you're calling your function. If you are flexible, taking advantage of the flexibility of the language when you're writing your function, you're going to have to take great care when you're calling the function to check what it's returning to you. One or the other. You can't ignore both sides. Yeah, and just terminology wise, the declaration is the first line where you say, here's the name of my function, here's the parameters it's going to take. That's the declaration. The definition is that plus all the lines of code that get executed when you call it. And some of these things they mean more, they're more significant in other languages. For example, in C++, you have two different things. You have the declaration. At the end of the declaration, it's a semicolon. It's a line of code by itself. And then there's the function definition, which is repeating that first line with all the code that goes with it. So declaration and definition. But in Python, it's all one thing. You define and declare and define the function in the same thing. Parameters, you'll probably hear me say arguments. Sometimes the book may use the word parameters and arguments interchangeably. The only distinction I've ever heard is maybe your parameters are the list, the declaration declares the parameters, and the values you pass are the arguments. I've heard people use that distinction before, but for the most part, they're just used interchangeably. Parameters, arguments, whatever you want to call them. Yeah, so as I said, there's no specific return type. Again, and I hate to keep preaching on other languages, but it's important, like I said, in this class to give you a broader sense of how this stuff works. For example, in C++, you declare what return type a function will return. And if your function is defined to return an integer, and you have a return statement in that function that returns a string, you're going to get an error right there. The C++ compiler is going to tell you, hey, you're breaking your contract. You said the contract was that this function was going to return integers, and right here I can plainly see that you're returning a string. So it's going to call foul right there, as opposed to going ahead and saying, yeah, Python, we'll just return whatever you want to return, and the caller has to be diligent in figuring that out. There's such a thing as a void function. You can pass, you can return integers, you can return strings, you can return other stuff, or you can return nothing. You can just say return. And we would say we're returning void, returning null, etc. And where you would see that is the pattern of, hey, can you do some work for me? Like at the beginning of your program, you may say, print my standard welcome to my program message. And you put that function in every one of your programs and you call it, and hey, it always does that work. You don't have to think about it. Or report headings. They're always the same. It's just a bunch of static text. So you get to a certain point in your program and you say, yeah, call the function that prints the headings. Okay. But it's fire and forget kind of code. And so, like I said, you can litter your function definitions throughout your code, but it has to occur before you call it. You can't have the call up here at the top and then define it down here on line 120. It has to be defined before it's called, similar to in Flowgorithm, how you have to declare your variables before you can assign them. And I'll be honest, I find that makes the code less readable. I don't like languages where you open up your source file, like your Python program, and the first thing you see is a dozen functions. And you have to scroll down, scroll down, scroll down, scroll down. And then finally down here at the bottom is your main function or your global code that does all the calls, because all that code has to be after where all the functions are defined. I don't like it. That's the thing about C++ is you have your function definitions. You can put those at the top or even in a different file out of the way. And then those definitions can be anywhere, maybe not even in the same file, as long as you know what the signature of the function is, so that you can call it. But it is what it is, just a difference between languages. Okay, so built-in functions, we've already used a bunch of them. You know, print, stir, int, input, all of those should be familiar to you by now. If you go to W3 Schools, there's a nice list of all of the built-in functions. Some of them you may not have ever used yet or had a need to use, but I would say it's probably good to go to that and just read each one of those lines and say, oh, really? I didn't know Python had a function that could do that, and just be familiar with them. And one of these days you'll have a need for it and you'll think, oh, wait, what was that function? There was a function in Python that would do that for me. Yeah, so this is an example of using a function, defining and using a function. Let's say the problem is, I'm going to pass you how many pizzas are going to be bought and how many Cokes they're going to want to drink. And you format an output message that displays the price that they're going to need to pay. Okay, so here's my contract. I've got two integers, right? Here's how many pizzas. Here's how many Cokes. And my expectation, my contract, is that that function is going to print a message and then return nothing to me. That's my contract here. Because that's what I needed to do. That's my problem right there. Yeah, so like I said, this is going to create a void function because we've not asked for a return value from this function. So this is my first line of my function. It's my function declaration. Starts with the keyword def. That's how Python knows, oh, you're about to tell me if there's a function here. Here's the name of the function, and here's the list of the variables, the parameters, the arguments that it's going to expect. So whenever I call print message function, I have to pass it two values. Do they have to be integers? Do they have to be strings? Do they have to be lists? You know, Python will allow me to pass anything here. Now, whether the code that I write in here is going to work based on what I passed it, that's another matter. Like I said, diligence with what I pass means I can relax with what I accept. Relaxing with what I pass means I have to be diligent with what I accept. So this is going to have a couple of lines of code. One is going to calculate the cost. Again, this is just a fake problem, but the number of pizzas that you pass in, I'm going to multiply that times $9.99, smoking hot deal, get them while they last. And the number of Cokes, I'm going to charge you $1.59 per Coke, which seems like that's actually a pretty good deal from the places I'm eating at these days. Can't even get a Coke for that at McDonald's, it seems like, for $1.59. Okay. So then here's my print statement. And I'll let you figure out what the fancy formatting code says there. Anybody got a guess? What does this do? Okay, well, all it says is I'm going to create a string that starts with a $sign and a space. And then I'm going to have a decimal value, right? Dollars and cents, two decimal positions, and it's going to be a total of 6 characters wide. So it's going to be right, justified. So to call that, here's an example of calling it. I call print message. I'm going to pass 0 and 2. Now, again, the flow of my Python program, if this is all in my Python file, is it comes down here and it skips this, and it comes to this as my first piece of code in global scope. And it's a function call. So it will jump back up here, execute these lines of code, and then jump back to here. It's how the flow works. It's just how Python works. So if I just ran this program by itself, it's going to print one line to the screen, and it's going to be $3.18 if I did my math right. Here's another call. I pass 1 and 0. I get $9.99. I call it again with 2 and 4. I get $26.34. Easy cheesy, right? The only thing I'm demonstrating here is code comes down here, it jumps up, it executes these 2 lines of code, comes back. Executes this, jumps up here, executes these 2 lines of code, comes back. Jumps up again, executes these 2 lines of code, and comes back. Boom, function calls. Here's a better version of that program. I'm going to pass it the number of pizzas bought and the number of Cokes, just like before. But instead of doing the print statement, it's going to create the string and return the string as a return value. I like that better because I don't like calling functions and the functions do print statements. It just makes the hair on the back of my neck stand up. I just don't like it. I like for my main function to be in control of what the user sees. I want to call functions and have them do stuff for me and give me the data back. Call another function, have it create the message for me, return it, and I get to print it. I just like that flow better. So here's the same thing. I renamed it. Instead of print message, I said get message. You know, your mileage may vary, style. Same thing though, it's going to accept the number of pizzas and the number of Cokes. And instead of printing the string, it's just going to return the string. Which means my calls are going to be a little bit different. I'm going to wrap them with a print statement this time. But same thing. Right? It does the exact same thing as the previous version of it. I just like this one better. Keep the print statements out in the global or on the main function. Okay, here's another example. If I pass you a student's current percentage grade, they're making 85% or they're making 92% in the class right now. And I have to give you how many points possible. If we had, 500 points possible in assignments so far, or 200 points possible total so far in the semester. And then I give you, okay, we just had a quiz and there were 10 points possible and this student got 8 correct. So I have to give you those 4 values for you to be able to do this work. Then you give me back what their new percentage value for the grade book is. Everybody buy that? So percentage, that's going to probably be a decimal value. Total points, integer. And then points correct out of points possible, a couple more integers. So 4 values input, 1 value output, and it's going to be a percentage, so a decimal. Okay, here's my function definition for parameters. Notice how I've named them. Here's another thing that I want to point out too. Notice the naming convention I use with my functions has capitalization. Anybody remember what that's called? I think that was in what, chapter 1 or 2? And this is camel casing. I think I call it Pascal casing. Because when the Pascal programming language came out, that's what they used. So that's why I call it Pascal casing. But I think there was another name for it in the book. I just can't remember off the top of my head what it was. But it will help if you use that convention. Because whenever people see something current PCT, they'll know, oh, that's either a variable name or a parameter value or something. When they see something that's capitalized like this, they'll say, oh, that's probably a function name. Of course, I say that, and none of the built-in functions are Pascal case. They're all lowercase, so go figure. All right, so then I've got a bunch of math in here, and we could go over, this could be any number of things. We could be talking about that sphere program, and I could be calling a function to say, give me the coordinates of the next point that I need to draw, whatever, bunch of math. And at the end of it, it returns the new percentage value. So let's say they currently have an 80% grade. There's 100 points been possible so far, and they just got 19 out of 20 on the last assignment. So I'm going to call the update grade function with 0.80, 180, 19, and 20. So I fulfilled my contract, and they need to give me back the new decimal value. Oops. Yeah. I don't remember what the value is. I did the math, but I didn't put it on my slide. But you can do that, I'm sure. Copy and paste it, type it into Thawning or whatever, and you can see it. Okay, there's this cool thing called default parameters too. Python and other languages also allow this. Very useful. And what it means is you can call the function without passing all of the parameter values that are in the contract. So you can default on your part of the contract going in, basically, is what it means. The function, on the other hand, has to say, oh, if you don't give me a value for that, here's the default value I'm going to use. So the programmer writing the function is safe to write the code as if it's always passed a value. Because if anybody calling the function says, no, I'm not going to pass that value, well, I've already defined what the default's going to be in that case. So I can assume that a value always came in. The other thing is, if I've got my previous example and it's got 4 parameters, if I make the second one of those a default, they all have to be default after that. I can't have the second one and the fourth one be default. And because then if I only enter 2 values, I have no idea which the second one is. It just doesn't make sense. So here's an example, another get price function. I have a pizzas and a number of pizzas and the count. So I'm going to assume if you don't tell me how many pizzas were purchased, then I'm going to say 1. And if you don't give me a price, I'm going to assume it's $9.99. So I can just say pizzas times count times price. So if I just pass 2, then it's as if I pass 2, 1, and 99. If I say 2, 2, it's as if I pass 2, 2, and 999. If I say all 3 of them, then it's all 3 of them. Easy cheesy. Okay, real quickly, a little bit about scope. As these things become more esoteric, the topics, I'm going to probably go through them a little bit faster. We've got about 5 more slides left. I know this has been a long one. We're almost done. So with scope, think of it as if you're looking through a telescope. When you look through that, you see a circle, right? And the only things you can see are the things that fall within that circle, right? Call that a field of view, right? You're not going to see anything that's outside of that field of view. And it's the same thing. That's what we're talking about here with program scope, is you can define stuff, but you can't see it outside of its scope. So then we just need to know what the rules are. And in Python, we define blocks of code with indentation. So it's essentially with indented blocks of code that's indented the same level. If you define variables inside that scope, that indentation block, you can't see those variables outside of that block. Before or after, you can't see them anymore. It's like they don't exist. They only exist inside that scope. Okay. Let's say you got a loop, a while loop or a for loop. All the code inside there is indented, right? So if you define a variable result or average or sum inside the loop, it doesn't exist outside. Inside a function, same thing. If you define a variable inside a function, outside it, you can't see it. It doesn't exist. So if you want any data from inside the function, that's where you start thinking about your return values and return them. Yeah, if you define variables at the far left, we talked about that, lines of code at the far left, not indented at all. We call that global scope. And so anything can see those. The scope is global at that point. Other languages, we might use the term static. Static and global can be synonymous. If you have like C++, where you can have a bunch of files that all get compiled into one executable, then you can have what's called file scope, where if you define a variable, a global static variable inside a file, you can't see it in the other files. There are ways to get to it, but by default, it has file scope, but we don't have that here to worry about. Where this gets interesting is, let's say you have two functions, and each of those functions define the variable average. You know, one does the average of a bunch of integers, and the other one does the average of a bunch of floats, or one does the average number of pizzas, and the other one does the average number of beverages. You can reuse the variable names in the two functions. You don't have to make every one of your variable names unique globally. You just have to make them unique inside a function. That's nice. But you can also have a global variable and that same name used inside a function. Okay, that's interesting. Which is it going to use? If you say print that variable name, which one of the two is it going to use? The one defined in the function or the one defined globally? Well, it's going to use the one defined in the function. And the rule of thumb there is it's going to use the one that's defined the most closest to that line of code. So inside the function is closer to the line of code. So it's going to use that one. If you're writing your code inside your function and you need to get access to the one that's global also, and you don't want to rename your variables, you can do that too. You just have to use the syntax. You just have to use the global keyword. And that's in your chapter. There's an example of that. I'm not going to assign any projects where you have to do that because it's weird. Here's another thing that you just kind of need to know and file it away. It'll be very important when you're learning new programming languages, C#, Java, whatever, is this by value or by reference. When you hear that, what we're talking about is simple data types, the ones we're familiar with, int, string, float, list. No, not list, the simple ones, int, string, float. Those are passed by value. When you call a function and you pass those values to that function, you're copying it and passing a copy to the function. It would be chaos if you passed a variable to a function and that function had the freedom to change the value of it on you. So when you return from the function, it's like, what the heck happened? I had the sum variable, I called this function, and the value of sum changed. What the heck? Then you'd have to be making your own copies of the variables before you pass them to functions. And we just said, no, that's just nonsense. So for simple types, when you call a function, Python will create a copy of that for you, and the function is working on the copy. They can reuse sum, they can set it to 0, they can add their own stuff up all they want to. When it returns from that function, your sum variable is intact. It has not been modified. Okay, that's passed by value. It passed a value to the function, not the variable itself. As opposed to the more complex composite types, list, dictionary, other classes and objects you might define, those are passed by reference. So for example, that's what allows us to say, I'm going to pass this function a reference to an empty list, and it's going to go ask for a bunch of values from the user and populate that list for me. And when it comes back from that function, hey, I called it with an empty list, and when it came back, my list is full. So that's allowed. That's passing by reference. I'm passing a reference that they can use to modify. And when it comes back from that, I've got the data. 3 more slides. Yeah, I'll point out again on the whole structured, unstructured argument. Passing by reference is a way to create some really insidious bugs. In computer science terms, we call that side effects. When you call a function and something in your world changed because of calling that function, that's a side effect of calling that function, and it's bad juju. Unless you expect it to happen, that can be bad stuff. What has happened traditionally is memory corruption, a buffer overrun, or any number of other logic errors that happen inside that function, and data that you thought was protected suddenly got corrupted, overwritten, or whatever. So when it comes back from the function call, your code goes haywire, your loop runs infinitely, whatever logic issue happens because of these side effects. There are languages, I think F# is one of them, where side effects aren't allowed. Everything's immutable, which means non-changeable. You declare a variable, it's got a value and it doesn't change. You might think, well, how the heck do I do a loop in F#? Well, go read about it. Because there are ways of doing all the things that we know we need to do as programmers in those kind of languages. It's kind of like opening a book on quantum programming, right? It's just new and different, weird, and you just got to learn the rules in that environment. But just beware of side effects. Beware of calling functions and passing things by reference and weird things happening. And so that's pretty much it for functions. We talked about built-in functions, imported, programmer defined, a bunch of modular stuff, ways to call these things. One of the cool things that I think I skipped over is when you are doing a return statement, when you return from a function, you can return multiple stuff. So you can return 0,5, and you're returning multiple values to the caller. So that's kind of nice. That's handy. Other languages don't have that kind of thing. If you want to return multiple data values, you have to declare a class and return an object. There's some newer features that make that a little bit less tedious and annoying, but it's a cool thing about Python. One of the benefits that you get from its flexibility and the way the language is defined. But I wanted to mention that too before we go too far. Any questions?
Nope.
Thank you for bearing with me. This was a long one, and I will call that good. Okay.
So we're only gonna have like one more project.